pixel, 1 kilometer data, single daily measurement is pretty high. And the only way we can get this value, this is micrograms PIC per liter, the only way we can get that value lower is by using multiple pixels and averaging over different space and time scales. And so that's what this table shows. If you time bin the data, or if you look at different spatial bins, here is that 14.9 micrograms, but taking advantage of n to the square root of n, you can get the errors here down to values which are comparable to the concentration in the most oligotrophic regions of the ocean. So that's the 14.9, and this is a concentration representative of an oligotrophic area. But notice, we have to average over a month and 36 kilometers to get there. So, any questions at this point? Got a little diversion here. When we were doing this, the problem when you reserve a ship to go out and you say, I'm going to find a coccolithophore bloom, and then that's exactly when Mother Nature throws a curveball, says, oh, for the next 10 years, there's not going to be a coccolithophore bloom in the Gulf of Maine, which has been the case. Or 15 years. We haven't seen a big bloom since 2003. There are lots of, I could talk for another hour about that. But, so we came up with this idea of ChalkX, and based on the fact that blooms are relatively rare events, and we decided to make a do-it-yourself coccolithophore bloom. It doesn't take much chalk to make a patch visible from space. In fact, 13 tons of chalk was all we needed to do this. And the size and shape of the chalk that we got, which is mined from the White Cliffs of Dover. Okay, so we actually went to the company that mines this stuff. The whole Western European, all of Western Europe is built on about 1.5 miles of calcium carbonate. And so the White Cliffs of Dover, it ends at the White Cliffs of Dover, and there are companies that use this chalk for cleaning up oil spills, all sorts of industrial applications, paper whiteners. And so we thought, wouldn't it be cool if we could plan a deployment for a clear sky day and make a feature, and then we would look at all the processes responsible for what happens to that. So yes, we could see it from space, big deal, but if we could put sediment traps below that, and if we could look at how much of it gets grazed, how much of it aggregates, how much of it gets subducted physically, so it's lost, there's nothing physical is happening to it except it's being subducted under the sea. That would be an interesting scientific endeavor. So we had to go to the EPA and the Coast Guard for environmental impact statements, and we told them that when a quarter of all the marine sediments on Earth are chalk like this, they settled down. I'm not sure we could do this these days. So here's what it looks like. This is ground up, but basically the mean size was about the size of a coccolith. And here is the concentrate. This is our calibration for particle backscattering versus the amount of chalk. Pretty good calibration curve. And the size, the half 50% point here on the size is 2 microns, like a coccolith. So we thought this would be good material to do. So here we are preparing for that with our bags of chalk, and we had the customs guys. This is just after people were sending dust through the mail. What's the anthrax? Yeah, and so these guys thought we had bags of anthrax, and we told them we had a lot of birthdays, and that's flour for the cakes. And here we are steaming in an elliptical pattern here. We're spreading it. We had tanks here that we loaded it into, and then we had to disperse it and then put it over the side. And that was it wasn't quite as homogeneous as we would have liked, and you can see by the time we finished, laying this, it was already starting to not resemble an oval shape. Here's the Endeavor, and we had radiometers mounted on the bow and on the superstructure. And here was the MODIS view when we did, in that little spot right there, that's our patch. And 2 highest pixels, basically, we were able to see. Now, that's all well and good, but what happened to all this chalk? The chalk, the major aspect of what happened to that chalk, very little of it fell into sediment traps, almost not measurable. Very little of it aggregated. We had these couette flow containers that we were making aggregates by shearing the water. Not very much wound up. We did see it in some organisms. It was getting grazed, but it wasn't much. Most of it was subducted. It was spread into a thin layer about 2 meters thick and 10 kilometers wide. And so in the course of about 72 hours, this patch basically was physically driven, and we made a thin layer out of all that material, which is really interesting because it says that for a coccolithophore bloom to happen, there have to be enormous production rates of this material, that the cells are producing calcite at fast enough rate that dispersal, normal dispersal, won't just take it away and put it into a thin layer. And we were using the ship to look at the distribution. This is based on radiance measurements. Okay, I'm up to about an hour. I have a little bit more, but I don't want to bore you guys to tears. Do you want to take a break, or I'm not. See, take a break? No, keep going. Okay, so. Okay, all right. Yeah, no, I won't go up to them. This is a really important paper. If you're interested in coccolithophores and their distribution around the world, this goes back to 1967. Andy McIntyre and Ellen Bay basically described distributions of coccolithophores. It's a huge amount of work that these guys did to document the floral groups of coccolithophores in the Atlantic basin. And one of their prime plots in this is that they found these different floral groups, species. They were interested in it from a geological perspective. But, if you're looking at them from space, you need to be aware that not all the same species, when you're looking at PIC from space, it's not all the same species. And there are differences in distributions. Some of them grow high in the water column, some of them grow down deep. And they're tropical species and so forth, and up to subarctic and subantarctic. So in doing our Atlantic meridional transit cruises, and these are a whole bunch of the cruises that we've done, we've looked at things like this. And we've looked at the ratio, for example, of PIC to chlorophyll as a function of latitude. And I show all the different water masses here. This is south equatorial countercurrent, north equatorial countercurrent. North is up here, south is down here. And the point I want to make is, as a ratio of PIC to chlorophyll, so you've got your primary absorbing molecule, chlorophyll, and your primary scattering molecule, calcium carbonate, in the central gyres, that ratio is highest. There's the least amount of chlorophyll, and there's the most amount of PIC. So while you might think that the subtropical gyres are biological deserts, relatively speaking, there's a lot of calcium carbonate out there that's affecting the water leaving radiance. And there's a peak in subantarctic waters, peaks in the gyres, and it's low at the equator. And that's another important part. A lot of people will say, yeah, there's major calcium carbonate production that happens at the equator, but at least in these waters that we've been in, the lowest concentrations of PIC that we see are actually at the equator. Lowest ratio. I've got plenty other data I can show you. In fact, I think I have a plot here. And here is backscattering, acid labile backscattering to total backscattering, particle backscattering. And you can see this ratio here, about 40 to 50%, 40% of the backscattered light is from calcium carbonate here in the North Atlantic Gyre. In the South Atlantic Gyre, numbers are maybe 20 to 30%. And there is a little peak here at the equatorial upwelling that happens. And then there's these very low values here, almost back to zero in this region here at the north equatorial current, for example. So that's what I just said. And now this gets back to your comment, Ken. These are the mean section of coccolithophore counts. These are numbers per mil. It's a log scale. A section that goes from 60 north down. Most of the data are at about 45 south. And look in the surface waters here at the equator. We're down at below 100, certainly, 40 to 50 cells per mil. And now down here in the southern part of the South Atlantic, concentrations upwards of 150 to 200. These are not blooms, but there clearly are more here than there are in this region around in the equator, which is a real surprise to me why there aren't more, because it's predominantly an upwelling region. But that's another story. Yes? Biomass of, or the mass of calcite? Let's go back. So this one? Yeah, this is one cruise. This is one cruise. So in the high, so the 45 was about here, and again, this is a ratio to total. It's the same ratio thing. So this is the ratio of acid labile backscattering to the total particle backscattering. So it's not the absolute amount of a BB prime. It's there's other organic matter and other. Yeah, good question. And for coccolith concentrations, so these are individual coccoliths. Notice the difference in magnitude. The lowest is 1,000 per mil, okay, on this. That's down here at about 500 meters. So these are here 1,600 per mil. This could be dissolution that's happening. The particles are sinking down deep. And here is the high value at both ends. It's not as strong a decline at the equator as we saw for coccolithophorids, and I think partly it's probably related to the fact they sink so slowly and things are generally just more mixed. And notice here there are subsurface populations here. So there are species of coccolithophores that live down. These are down at 150 meters. We have, these are the coccoliths. If I go back here, you can see some evidence of subsurface populations here, down 150, 180 meters. There are species that live below the 0.1% light depth, Fluorosphaera profunda. Profunda is because deep. And there are, what is allowing them to grow so deep is probably that they're mixotrophic. They don't live a photosynthetic existence exclusively. This is a new paper that came out. This is in progress in oceanography. It's a paper by Poulton et al. And there's a lot going on here, but just to say they're different species at different depths. And so each of these, this is abundance, normalized abundance, and he shows that different species live at different depths. Here's your Fluorosphaera profunda here, and you're looking at depths. This is at 6 optical depths here that he's divided this, and it goes down to 10 optical depths, and he sees that's 0, so none at 11 optical depths, but he's seeing some down at 9 optical depths. So they're very deep. No, this is Alex Poulton over in the UK. Okay, and just when I thought the North Atlantic stuff was as big as it got, then we started looking at remote sensing data all the way back to CZCS, And we saw this feature down here, and we said, you know, come on, this is probably being fooled. The algorithm is being fooled. We all know that it's all the sediments, at least down in the southern end down here, are all opal sediments from diatoms. And so we planned a few cruises to go down there and see. We've had 3 cruises, one focusing on this region, one focusing on the Atlantic sector down below the polar front, and one focusing on the Indian sector. That region, which is of interest, here's what the water looks like over the Patagonian shelf. Here's a radiometer being lowered in, clearly turbid. And what do we find there? We find coccolithophores all the way across. These are in extremely high densities on the Patagonian shelf. And I superimposed some SEMs, just nothing like having pictures to see. It's not exclusively coccolithophores. There are different species. The diversity increases as you head to the east. But there were features associated with fronts, and I actually have translated the color front here, down below here, to the SST image, just to show here's the subtropical front in red. Here's the subantarctic front, which this is the color front associated with the calcium carbonate, and here's the polar front, which is a color front as well. And so there are distributions of these coccolithophores that are associated with the stratified side of these various fronts. And remember, I talked about CO2. So coccolithophores actually make CO2. They take 2 molecules of bicarbonate, they split, one goes into calcium carbonate, and the other goes into CO2. And so here is a transect that we ran, and PCO2 concentrations shown in these colors. And here we are north of the color front, and then as we go into it, we see the PCO2s, the highest values, the red value here, the red values and the yellow values. The lows are these blues. And then this is a climatology we superimpose these on, so it's not absolute. The climatology shows some amazing structure here, not that fly. And here, this is a 12 or 14-year climatology, consistent regions of low PIC, at least in the NASA imagery. But there are some areas here where we get up to 420, 430 ppm, microatmospheres for CO2. So, climate change effects. It's happening. The climate is changing, and things like ocean acidification is happening. There's more acidic water. It's harder for these organisms to calcify. First waters to be subsaturating to calcite will be high latitude polar waters, and this is related to the chemistry of the bicarbonate system, but that's a fact of life. The areas, and there are areas in polar waters now that are very close to being, that are subsaturating for aragonite, and they are getting close to subsaturation for calcite. Even in the Gulf of Maine, we see times of year, in the very coldest times of year, where it is subsaturating for calcite. So that's in months of January to March, when the coccolithophores wouldn't be blooming anyway, but it is just worthy of note that in the Gulf of Maine there are regions where the waters can already be subsaturating. Coccolithophores are favored by warming polar waters, and there's some people that are saying that they're advancing north, and they're increasing the high latitude biological pump. The poor coccolithophores are kind of between a rock and a hard place, because the water's warm too much, they won't be happy. And as they go further north, the water is more corrosive to calcium carbonate. So anyhow, here's a paper that came out last year by Rivero-Calle et al. In Science, and they were using the continuous plankton recorder data that go back to 1965, and they're looking, the nets on those CPRs are very broad, they're silk, but they capture coccoliths, and they look at these nets under the microscope, and they look at the probability of seeing coccoliths in those nets. And basically, they've seen since 1960 the probability actually going up. More coccolithophores are being formed in the North Atlantic. And here is the probability for coccolithophores here. They're looking at CO2 concentrations and Atlantic, these oscillations. But the take home from this is, in this paper, basically it's evidence that coccolithophores are fighting back. They're, and diatoms, interestingly, are actually going down since the 1960s. Yes?
Just so the class knows, the author of that paper.
She's really good. Okay. PIC Global Time Series. This is what, if you take all the MODIS Aqua data and you look at the integrated amount of calcium carbonate in the top 100 meters, and I don't have time to tell you how we estimate that, but and you see annual cycles. And every January, this is the austral summer, you see the peak in global calcium carbonate, and this is in moles of PIC. And so the southern hemisphere dominates the PIC cycle on the globe. Here is this is the the summer solstice in the northern hemisphere. It's actually at a low point, globally speaking. And the equinox, we have these little peaks here associated with the March equinox that happens every year. So, summary of the optical properties. The absorption is minimal for calcium carbonate. There may be some down in the UV. The scattering is high. It can be a first-order contributor to water-leaving radiance. The scattering cross-sections are variable and likely species-dependent. The birefringence is strong, but beware of non-calcite birefringence particles. Mesoscale high reflectance blooms are immense and are found mostly at high latitudes. Why should you care about coccolithophores? They're primary ballast material for driving the biological pump, and half of the anthropogenic CO2 that we humans have produced is gone to the seafloor, care of the biological pump. On short time scales, they can be producers of CO2, and suspended coccoliths found throughout the ocean increase the ocean albedo, but they also can increase the warming rate. So those of you who are interested in more physical aspects, because there's multiple scattering that happens, they actually, there are papers, Steve Ackelson wrote a nice one, where the warming rate is noticeably higher inside a bloom, and over the course of 2 weeks, that change in temperature can be significant. Warming and stratification will likely enhance coccolithophore growth. Coccolithophores may be sensitive to ocean acidity, which is a minus, which in the changing Arctic may limit their advance, but the paper by Calle Rivero basically suggests that at least over the last 50 years, they're on the increase. Importance of satellite remote sensing of coccolithophores. Satellite record is not yet long enough to see any trends in the abundance of coccolithophores, at least as predicted by the models. We're getting there, but you know, there's a lot of variance from year to year, and so discerning that variance is tough. Continued satellite ocean color remote sensing will be the best way synoptically to follow the fate of these plants through time as the planet warms and the oceans acidify. And I'm going to end with this. So this is basically a time series. Let's see if it should start on its own. And it'll take you through about a decade. Let's see if I click on it. Maybe it'll start. Well, I thought it would start. Like, maybe I have to. Yeah, there's the mouse. Let me go back and, well, anyhow, if it'll start, you'll get to watch the seasonal patterns. And I didn't mention, this area down here that I was showing of high calcite, we call it the Great Calcite Belt now, because it really does appear to be related to the abundance of coccolithophores. So I'll quit there and take questions. And yes?
You said that you mentioned that of the biological pump. What is the contribution of coccolithophores? Because you also said that they extract CO2, right? While
Yeah.
making the shell.
Well, they can produce CO2 actually while they're making their shell. So that's the part with the alkalinity pump. They're pumping some of that bicarbonate in the surface ocean to the sea floor. That bicarbonate in the surface ocean is in equilibrium with CO2 as well. So CO2 dissolves in seawater. It becomes part of the DIC equilibrium, and so as you increase the amount of CO2 in seawater, there will be more bicarbonate. But to answer your question, the big effect of the coccolithophores specifically, so diatoms are also a major part of the biological pump. And there are a couple of different studies that show that the diatoms are responsible for, you can also relate the diatoms to the absolute flux. But what Francois and others, Phoebe Lamb has also shown in a nice paper 2 years ago, her student Sarah Rosengard, that the efficiency of the biological pump, not the absolute amount, but the efficiency increases. And that's what Francois showed in that figure. The efficiency of the biological pump goes up in the presence of calcium carbonate. And so that's to say that the highest absolute fluxes are not always where coccolithophores are, but where you have high coccolithophores, more of that POC will be exported to depth. Whereas diatoms correlate quite well to the absolute flux. Where you have a lot of diatoms, you will most likely get a high. So both mineralizing phytoplankton, very important for export fluxes. Yes?
You really need the ocean color to detect coccoliths? Or could you use broadband or?
So there were, 11 years? CZCS died in 86, and CWIFs didn't go up until 97. So there were 11 years where we didn't have ocean color. And so that one image I showed you of the North Atlantic, that was from ABHRR, where there's this really low sensitivity, broadband visible channel, which we kind of bootlegged and used that, and we had a quasi-atmospheric correction. We'd subtract out one of the infrared channels, and we were able to visualize that little movie loop I showed you. That was all based on ABHRR data, because we didn't have ocean color, but ocean color makes it way more precise. Yeah.
That gives you a long span.
Yeah, and it's the radiometers aboard the ocean color instruments are just way better validated and such for doing these. There's someone else today. Yes.
I was wondering what the reason is for the relatively high PIC among the gyres. Is it just that coccoliths get into the gyres by the target?
So the gyres they're fairly well stratified. Okay, and keep in mind that there are different ecotypes. There are surface dwellers, there are mid-euphotic dwellers, and there are sub-euphotic dwellers, and so there's that aspect. They're not all like E. huxleyi keying in on one type of hydrographic condition. The coccolithophores have this ability to grow in low iron conditions in very low nutrient concentrations, lower than certainly lower than diatoms. So where we find them, for example, at the subtropical front, or better still, the polar front. Take the polar front, for example. Diatoms abound south of the polar front at 60 south. And there's a fair amount of iron in that water, iron that's coming off of continents, and the distribution of coccolithophores. I actually can show you that. If you look, where is it? Right here. And so here is all the way around the globe, minus 180 to 180. And this is in the region of, I think it was 40 to 55 south, something like that. Here is PIC concentration. So we basically chopped, here's the tip of South America, Africa. Let's see, I have to look at this. Here's the Patagonian shelf. Yeah, this is South America. Africa's over here. Australia's over here. And we are looking at, for different seasons, so this is PIC per 10 degree latitude by 10 degree longitude box. So we divided up this section all the way around the world. And you can see as we get close to the land masses, we see more coccolithophores. Here is the Crozet and Kerguelen plateau. Here's Australia over here in New Zealand. And here is basically, so the impact of, I think, dust coming off of South America, the Patagonian Plateau. Here is, this could be South African, or related. Here's South Africa. We also see a bump up around the Crozet and Kerguelen Plateau. And off of New Zealand, we see the numbers go up. So each of these are a different season. And the lows, the austral winter, are these yellow points, and the austral summer are these blue points. So in the subtropical gyres, you have the situation where you have organisms that can survive in very low iron conditions, and they're not being competed against by abundant diatoms, and I think that's how they survive there. Chlorophyll levels are not very high at all, but their relative proportion of calcite to chlorophyll is large. So calcite plays a huge role in the radiometry in the subtropical gyres, or a larger, proportionally larger role. Others? Yeah. New algorithm is a difference algorithm. So we've been working with Schwamin Hu, and basically have come up with, this is with Catherine Mitchell, my postdoc, and it looks pretty good. It's nice, and so it's in review right now. So, okay. Anything else? Thank you, everybody.